classes in variations of Hodge.
Okay, thank you. Yeah, so again, I said it already, but thanks very much for the invitation. I'm sorry to be disappointing everyone in the sense that I'm not talking about anything connected with drive categories. It is just a Hodge theory topic. So what I am going to talk about is something that has to do with a generalization of Hodge classes and a generalization of this famous theorem by Cattani-Deligne-Kaplan that sort of tells you about the set where some classes are Hodge classes. Okay, so I will start with the generalization. I will start with discussing a bit the Hodge classes and Cattani-Deligne-Kaplan theorem, and then I'll get to the new part. And the new part has some physics connection, so it's somewhat unexpected maybe. Okay, right, so let's start with a bit of review. So this theorem about Cattani-Deligne-Kaplan is about integral Hodge structures and integral Hodge classes. Okay, so I'm sure everyone knows an integral Hodge structure is you have some lattice, a free Z module. The complexification has this decomposition by Hodge type, and I want the weight to be even so that I can talk about Hodge classes. Right? And then for technical reasons, we're also going to need a polarization. So this is some bilinear pairing with certain properties. I'll say more precisely later on what the properties are for. Okay. The typical example from geometry is that you take a smooth projective variety and take cohomology in even degrees. Has an integral structure, modulo torsion, has a Hodge structure of weight 2k, and then the polarization is constructed in a slightly complicated way by cup product with a class of an ample bundle and integration. So a typical example would be, say, you take H2 of a surface, then the pairing is really basically just integration over x, except that there's a primitive part and a non-primitive part, and the signs are different. So there's something to do with the class of the ample of a hyperplane section, okay? Anyway, so the polarization usually looks something like this. And then an integral Hodge class is just a class that's purely of type KK in this decomposition. The reason why people are interested in these classes is because fundamental classes of subvarieties are Hodge classes. And well, then also everyone surely knows that there's the Hodge conjecture, which predicts that conversely, as long as you're on a smooth projective variety, at least some multiple of every integral Hodge class should be a linear combination of fundamental classes. Now, there's this multiple thing. This is because the Hodge conjecture is really a statement about rational cohomology. It is known by all kinds of examples that for integral classes, the Hodge conjecture is false. There's a lot of counterexamples, lots of pathologies, okay? But nevertheless, the thing I'm talking about is about integral classes, even though the geometrically meaningful statement is about rational coefficients. So this is a sort of small subtle point. Okay, so what is this theorem of Cattani-Deligne-Kaplan about? Well, this is about families of Hodge structures, okay? So now I changed the notation slightly, and I let X be just a smooth complex algebraic variety. This is some kind of parameter space. And then over that X, I assume that I have a variation of Hodge structure, which is a notion of a family of Hodge structures. So roughly speaking, what you have is every point, you have a vector space, constant dimension with a Hodge structure on it and an integral lattice and a polarization. And then you want these things to vary nicely from point to point. So on a topological level, the individual Z modules, individual vector spaces form a locally constant sheaf. And then there's some other condition on how the Hodge decomposition changes from point to point. Again, the exact axioms don't matter for us now. But the typical example is when you have a family of projective complex manifolds, then you can take the cohomologies of the fibers, and those form a variation of Hodge structure. In that case, the local system is the higher direct image of the constant sheaf. Okay, and so now the starting point is the observation by Weyl that if the Hodge conjecture was true, so if Hodge classes actually came from subvarieties always, then in families, you would get some algebraicity statements. Namely, if I take a family y to x, like here, and I take an integral class on one of the fibers, and then I use parallel transport to move it to nearby fibers. And then I look at the set of points in the base where I get a Hodge class, where some parallel translate is a Hodge class, right? That sort of locus would have to be algebraic if the Hodge conjecture was true. Because if the Hodge conjecture was true, that would be a locus where some cohomology class is represented by algebraic cycles, and then the algebraic cycles have some algebraic parameter spaces. And from that, one can deduce with a bit of arguing that you get this is an algebraic condition. And the interesting thing is that even though we don't know the Hodge conjecture at all, people were able to prove this algebraicity fact. So this is a very big famous paper in 1995 by Cattani-Deligne-Kaplan. They showed that this algebraicity thing is true. In fact, they don't just prove this in the geometric setting for variations of Hodge structure coming from families, but they prove it for arbitrary non-geometric variations of Hodge structure. This is very useful because when you're looking at questions about families or about moduli spaces, this statement is almost as good as the Hodge conjecture, right? You don't get information about individual smooth projective varieties, but it says that in families, if you look at loci defined by Hodge theoretic conditions, they will be algebraic loci. So for example, you can go to some moduli space. In that moduli space, you look at the set of points where some kind of Hodge theoretic thing holds, and that will be an algebraic subvariety of the moduli space. This is the sort of application of it. And it also has some small arithmetic implications that were studied by Voisin. Okay. Anyway, so I want to give actually the precise statement because this will be the sort of thing that I want to generalize. But so the precise statement is actually even stronger because they don't just look at the locus of points in the base where some class is Hodge, but they also keep track of the classes themselves. Okay. So in order to do that, I need this vector bundle. This might be called the Hodge bundle or something. This is the vector bundle whose fibers are the complex vector spaces in which you have these Hodge structures. That's originally a complex vector bundle. It actually has a uniquely determined algebraic structure always. And so that's kind of the space, right? And so inside of this space, inside of this bundle, what they do is they look at Hodge classes. Okay? So you think of points in this bundle as a point in the base and a vector in the fiber. And then you can define the locus of Hodge classes. So this is the set of classes in the fibers where you get an integral Hodge class. Right? You have a point in the base, and then over that you have a vector in the fiber, and you want that vector to be integral and of type kk. And then to make things sort of tractable, you also impose this condition here, that so the polarization, this bilinear pairing, that the value of that pairing on this class should be constant. You think of this value of the pairing as some kind of self-intersection number. This is sort of some topological quantity associated with that class, right? Again, in the case of a surface, this pairing is just cup product of V with itself on H2, for example. This is really the self-intersection number of that class. Okay, and so what they prove is that this locus, the set of points in this bundle, is an algebraic subvariety, even though the bundle, well, using the algebraic structure of the bundle, even though the conditions defining it are not at all algebraic initially. And also you have some finiteness. The projection from this locus down to X is proper, and the fibers are finite. Okay, that's the statement. Any questions on this statement? Okay, so this is really a very big theorem, but it's also surprising in some ways because it is actually much stronger than what you would expect geometrically. So here's a quote from Claire from some survey article about Hodge loci that she wrote a couple of years ago. She says, well, this theorem in fact proves a result which is stronger than what is predicted by the Hodge conjecture. And the finiteness statement is intriguing because it is not predicted by geometry. Right, again, the point is that in the Hodge conjecture, it's a statement about rational classes, and all kinds of things are false and pathological with integral classes. Nevertheless, this is a statement about integral classes. And also, there's no good geometric reason to expect this kind of finiteness. Why putting this condition of bounded self or fixed self-intersection number should suddenly make things finite. Okay. Let me explain a little bit the easy part of it so you get a feeling for for this result, okay? So the easy part is the fact that the projection has finite fibers. The difficult part is that it's algebraic and that the number of points in the fibers is sort of uniformly bounded or something like that. But the easy part is that just each fiber by itself has finitely many points in it. This is a very elementary argument, okay? So again, let me take an integral Hodge structure. And now I'm going to tell you what this polarization condition is. So for that, you define this auxiliary operator called the Weyl operator. It acts on this PQ space in the decomposition by multiplication by I to the P minus Q. Okay, so since the weight is even, P plus Q is even, this is always either plus or minus 1. And well, in a Hodge class is of type KK, so that's of course an eigenvector for this Weyl operator. And then the condition to be a polarization is just this one, that if I take this pairing and I change the signs on all the entries by this Weyl operator, then I get a positive definite inner product. Okay, so the original pairing is sometimes positive definite, sometimes negative definite. And if I change the signs according to this I to the P minus Q, then I get something positive definite. And then I get a norm called the Hodge norm by just pairing a vector with itself. And so you see, if I have an integral Hodge class, then the value of the pairing is actually equal to the value of the norm, because the norm is Q of CVV. And since V is an eigenvector for C, that's the same as Q of VV. So if you look at integral Hodge classes for which the value of the pairing is fixed, that's the same thing as looking at integral Hodge classes with a fixed norm. Right? And so because this is positive definite, that's integral points on a sphere of some fixed radius. So that's the intersection of something discrete with something compact, so that's a finite set. Right? So in every fiber of this bundle, you only get at most finitely many points. The difficult thing is somehow that when you approach the boundary, well, why could that finite number not somehow get bigger and bigger or something like that? That cannot happen, it turns out, but this is the difficult part. Okay. All right. Yeah, anyway, any questions? Good, okay. Right, so now let me get to the sort of newer part. So then the second part of the story starts in late 2019, because at that point, I got an email message from a guy named Thomas Grimm, who is a theoretical physicist at the University of Utrecht. And so he said, so, I know that you mostly work with Hodge modules and stuff, but I have some questions about some old Hodge theory paper, this paper by Cattani-Deligne-Kaplan, because I'm working on some physics questions, and I'm interested in something more general than Hodge classes, some classes called self-dual classes. And I looked at the Cattani-Deligne-Kaplan paper, and it seems to me that even though they use Hodge classes a lot, maybe the whole thing should actually work for these self-dual classes. And he asked whether am I aware if there are any generalizations of this type have been considered in the literature. And he also said that for his purposes, which are some string theory applications, it would be crucial to understand the generalization of some finiteness statements in Cattani-Deligne-Kaplan. Okay, so he has some kind of more general notion of some classes, and for them, he still wants some kind of finiteness. So again, let me explain what he's talking about, so what self-dual classes are. This is again defined in terms of the Weyl operator, okay? So the Hodge classes were classes that are eigenvectors for the Weyl operator. Now, the way the Weyl operator looks like in the even case is that the eigenvalue is actually just +1 and -1, and they alternate like this. On the middle part, it's +1, then it's -1, then it's +1, and so on. And so a self-dual class is just an integral class that's simply an eigenvector for the Weyl operator. Not necessarily of type KK, but just any type for which you get a +1. And then, of course, dually, you could look at anti-self-dual classes. Those are the ones that are -1 eigenvectors. Hodge classes are always self-dual, right? We just seen that. But there's other interesting classes. So, for example, if you go to fourfolds, he was especially interested in Calabi-Yau fourfolds for a reason that I'll explain. If you go to fourfolds, then classes of type 4,0 and 0,4 can also be self-dual. On surfaces, for example, classes of type 2, 0 or 0, 2 would be anti-self-dual, because on those you get a -1. So this is a much broader set of things than just Hodge classes. And well, what does the self-duality condition mean? So this actually, it is, I mean, as far as I know, it has no kind of geometric interpretation. Right? For Hodge classes, at least you have this fact that subvarieties give you Hodge classes, and maybe conjecturally any Hodge class could come from subvarieties. The self-dual classes don't have any geometric meaning, but instead you can sort of understand what they're doing in terms of this Hodge norm. Right? So remember that the Hodge norm is defined in terms of this pairing by changing the signs, by putting in the Weyl operator. And so from this point of view, the self-dual classes achieve some kind of minimization of this Hodge norm in the following sense, right? If I take any integral class, I can decompose it into its positive and its negative part. Right? The part of it that's in the +1 eigenspaces and the part of it that's in the -1 eigenspaces of C. And then if I compute the Hodge norm, well, the inner product is orthogonal. The decomposition is orthogonal for the inner product. So the Hodge norm of V squared is the Hodge norm of the positive part squared plus the negative part squared. That's clearly greater or equal to the difference. And the difference is just equal to the value of the pairing. Okay, so because of this simple inequality here, a class is self-dual if and only if the -1 part is 0, if and only if the Hodge norm is equal to the smallest possible value it can be, which is the value of this pairing. Okay, so a self-dual class is exactly one for which the Hodge norm achieves the smallest possible value that you can have, which is just the value of the pairing. Okay, so this is not a geometric description of these classes, but it still says that they're sort of minimal in some sense. Okay? And it turns out that the physicists care about them exactly for that reason. So here's like a little one-page summary of what I understand of what he's doing. I don't really understand it. I mean, when he sent me his original email, he sent me a couple of links to some archive papers, and it is just not understandable for me. But anyway, but so here's what I understand. So what he wants to do, what they want to consider is Calabi-Yau fourfolds particularly. And then their terminology for integral classes is integral fluxes. Fluxes can be self-dual, anti-self-dual. Well, because of how the Weyl operator works in degree 4, self-dual fluxes would be things of type 4, 0, 2, 2, or 0, 4. Anti-self-dual ones are type 3, 1, and 1, 3. Okay, and then what they're actually interested in is pairs, a Calabi-Yau fourfold, and then one of these fluxes. And they let X vary in moduli. And they impose the condition that V is self-dual of this type 4, 0, and 0, 4. And then this condition that the value of the pairing should be some fixed number, this naturally comes up in their setting as some kind of consistency condition. Right? The value of the pairing is just the integral over X of V cup V. And this can be computed in a different way in their world. And it turns out to be that this pairing is actually determined by some other parameters in the theory. So it is natural for them to look at pairs XV, where X is a Calabi-Yau, V is a self-dual class, and the value of the pairing of V with itself is fixed. And then it appears that the Hodge norm, this thing that's being minimized here, is some kind of energy. So that when you look at self-dual fluxes, when you look at a pair like this, where the flux is self-dual, what you're looking at is inside of some big space, you're looking at points that achieve some kind of minimum of this energy. And well, they sort of think that minimizing energy, the set where that happens should have some kind of nice properties. And so that's why they made all kinds of predictions about it. So in particular, there's some papers 20 years ago, so by Douglas and Ashok and Douglas, where they started predicting that the set of these self-dual fluxes that should come up should be finite always. And they checked various examples, and it was true in various examples. Okay, so this is roughly speaking like the way it shows up. Let me give you one more slide here with some small examples. So these are just some very easy examples, but to show what these sets can look like when you look at sets of points where some class is self-dual. In the case of Hodge classes, Cattani-Deligne-Kaplan said that you get algebraic conditions. But for these self-dual classes, you don't. You get very non-algebraic sets. So a typical example is you look at moduli of K3s. So I guess I'm doing unpolarized K3 surfaces, right? So the moduli space in that case is just a quotient of a period domain D by some group gamma, and it has complex dimension 20. This has a very simple concrete description because the 2-0 space in the Hodge structure is one-dimensional. You pick a generator for it, call it sigma, and then the period domain, which is basically the moduli space, is just a set of all of these sigmas up to scaling, where these two conditions happen. So sigma paired with itself has to be 0, and sigma paired with its conjugate has to be negative. So this is a 20-dimensional quadric in D, and then inside of there is some open set. Okay, and then I can take a fixed integral class on my reference K3 surface here, and then I look at the set of points in D where this particular cohomology class is anti-self-dual of type 2,0 and 0,2. So this would be it's not exactly self-dual, it's anti-self-dual, but this is a typical kind of locus like that, right? So what does it mean for it to be anti-self-dual of this type? Well, it just means it's of this type. It just means that when you look at the Hodge decomposition, you only have a component of type 2,0 and of 0,2. The 2,0 space is spanned by sigma, and the 0,2 space is spanned by sigma bar. So you're looking at the condition that V has to be some multiple of sigma plus some multiple of sigma bar. And then you can figure out what the multiples are, what the coefficients are by just pairing with sigma and sigma bar. And then you get this equation here, this particular equation. Q of sigma sigma bar times V should be equal to the right-hand side. This is not, clearly not a holomorphic condition or an algebraic condition in sigma because it involves both sigma and sigma bar. In fact, if you think about it, if you count the number of real conditions that this imposes, this is exactly 20 conditions. And so as a submanifold of this, as a subspace of this moduli spaces, turns out to be a totally real submanifold of real dimension 20. Totally real means that the tangent space at every point is just a real subspace. It never contains any complex directions. Okay, so this is sort of opposite to being a complex submanifold or to be an algebraic submanifold, sort of completely transverse to it in some way. Another kind of thing that can happen is something like this. So if I look at variations of Hodge structure just on the puncture disk, there's some toy models, some kind of simple linear algebra gadgets that you can write down that give you variations of Hodge structure. They're called nilpotent orbits. And for those, people in Hodge theory know how to compute everything, so you can just compute what these loci look like. And you can get things that look like this. So on the puncture disk, you can get the real axis, like the positive real axis. That can be the sort of set of points where some class is self-dual. Again, very much not an algebraic subset. Okay. Any questions? Good. Okay. Well, then maybe I will tell you what the result is now. So I will go back to the Cattani-Deligne-Kaplan setting. X is my parameter space. It's a smooth algebraic variety, a variation of Hodge structure over it of weight 2k. And then again, I look at this vector bundle, this Hodge bundle, whose fibers are the vector spaces. And I remind you that this is an algebraic vector bundle. Okay, and then we do exactly the same thing as in Cattani-Deligne-Kaplan. We look at the locus of points in this bundle, the locus of pairs in an X and vectors in the fibers, where the class is an integral self-dual class with fixed self-intersection number. Okay, I want to be integral, self-dual, it's an eigenvector of the Weyl operator, and the value of the pairing is fixed. And then what happens is that, well, it's not an algebraic set, so I shouldn't be saying that it's algebraic, but it turns out that this set is still nice in the sense that it's definable in an o-minimal structure, I mean the specific one Rnx. I will tell you in the next few slides what that means, but this is still, it's not algebraic, but it's still kind of close to algebraic and somehow nice. And by the same argument as before, the easy part that I showed you, it's the projection down to X still has finite fibers, because we're still, when we control this pairing for self-dual classes, we're controlling the norm. And it's also proper, okay? And then the thing that happens with these o-minimal structures is that you get very strong kind of finiteness statements. So if I have something which is definable in an o-minimal structure, and if each, under some mapping, if each fiber is finite, then the number of points in the fiber is actually uniformly bounded. This happens sort of automatically because of this definability. And so in particular, then we get this kind of strong finiteness for these self-dual classes that is predicted by the physicists. I say we, so this is a joint project with Thomas Grimm, the physicist, and then also Ben Bakker and Jacob Tsimerman. So this might be not surprising if you've been following the literature, because they're some of the people who started introducing definability and o-minimal structures into Hodge theory. So
can you relate
yes.
it to algebraic classes? Does it mean that the algebraic classes fit in such a locus, and how is it distributed there?
Yes, right. So the algebraic classes are in particular self-dual, right? So they will be inside of there. Now it turns out that on every component of this locus, the Hodge decomposition is actually sort of constant, more or less. So if I have one component and I have a point on it where the class is a Hodge class, then it's actually Hodge class on the whole component. So what happens is that some components of this locus will be the Hodge loci, and you got some other components that are not at all Hodge somehow.
Thank you.
Mm-hmm. Other questions? Good. Okay. Yes. So definability. So again, this is usually the content of some kind of lecture series. So I'm not going to give that lecture series now, but I'll just give some very quick definitions. If you want to do any reading about this, this business of definability comes from model theory in mathematical logic. So it's been going on for a couple of years that people have been using this in algebraic geometry. So for example, for the André-Oort conjecture and questions related to it. And then more recently, starting with work by Klingler and also Bakker and Tsimerman, they discovered that Hodge theory works well with this with these o-minimal structures. There's a nice book, Archie talk by Frezan about Hodge theory and o-minimality. And there's also a collection of lecture notes by Bakker from some lectures that he gave at the Hausdorff Institute a couple of years ago. So if you want to do any reading about this, those would be two good sources. Anyway, so this o-minimal theory is really about real geometry, real algebraic geometry or something like that, right? So what we're really looking at is subsets of Rn, not subsets of Cn. And so the description of an o-minimal structure, well, first a structure. So a structure is that for every dimension n, you specify a collection of subsets Sn that are sets in Rn. These are the so-called definable sets. These are the sets that you can talk about in your language. And the conditions are the following. So you want the definable sets to be closed under unions, finite intersections, and complements. So it's a Boolean subalgebra of the power set. You want all the algebraic sets, so the ones definable by polynomials, you want those to be definable. You want the product of two definable sets to be definable. And then you want the definable sets to be closed under linear projections. This is the most non-trivial condition. So if I have something definable in n+1 dimension, I project it linearly to n dimensions, then I want the image to be definable. And
so
then
does this mean
yes.
Does this mean it includes all semi-algebraic sets?
It includes, in particular, all semi-algebraic sets, exactly, because you can always, since we're doing the reals, you can always take sums of squares and so on. So once you have equality, you can also get inequality by the projection. And then you call a function definable if its graph in Rm plus n is definable as a set. Okay. So, you think of these definable sets as being, when you specify them, you specify some structure. I mean, there's many examples, right? But when you specify some structure, you have a class of sets that are sort of nice sets. And algebraic sets are always nice, but you want to have a bigger class of sets to be able to talk about more interesting things. Examples of structures that are useful in geometry are the following four. So first, the smallest structure that contains the algebraic sets, these are the semi-algebraic sets, like Aaron said. So you don't just include sets defined by polynomials, but you also allow inequalities. Then you can enlarge it to a structure called Rn, where you include also analytic functions. Now, analytic functions are in principle bad because they can have crazy boundary behavior. So the way you control that is that you look at restricted analytic functions. So you take a compact set, for example, the unit cube, and then you look at real analytic functions on this unit cube that are actually analytic on a slightly bigger open set. This is sometimes called an over-convergent function or something like that, because it converges in a slightly bigger set. And the structure Rn contains all of these. I can say functions on the unit cube, right? Because then I have, since I have algebraic functions and composition and stuff, I can then sort of enlarge the cube in all directions. So then I get any analytic function that's defined on something compact and is analytic on an open neighborhood with the compact thing. A third important example is where you also include the real exponential function. This is because a lot of stuff in geometry is somewhat described by exponentials. Mind you that the exponential function would be included in 2 if you restrict it to a compact set. The point in 3 is that we're doing the whole graph of the exponential function as a subset of R2. Okay? And then the biggest structure is this Rnx that appears in the theorem. This is some kind of amalgam of the two that contains both Rn and also Rx. So you have restricted analytic functions and also the exponential function. Okay. So yeah, I mean, there's tons of these structures. You can arbitrarily enlarge them by just you just always add a bunch of functions and then close it up under projections and stuff. But of course, usually you don't get something nice. So the point is that there's this condition called o-minimality that ensures that your structure is tame or well-behaved. And the condition is simply this, very innocuous looking. So a structure is called o-minimal if the only definable sets in dimension 1 are finite unions of points and intervals. The only set that you can define in dimension 1 is either a point or an interval or some finite union of those. This doesn't look like a strong condition, but it is because you have this condition of being closed under projections, right? So for example, if I have a definable set in dimension n, and I project it linearly down to something one-dimensional, then I have to always get a finite union of points and intervals. This puts some very strong constraints on what n-dimensional sets I can have. And well, fortunately for us geometers, the model theorists have put a lot of work into studying these. And they have shown that all of these 4 are actually o-minimal in that sense. So this is a not so difficult theorem in the case of R-alg. This is Tarski's theorem about quantifier elimination. And then the most difficult one is this theorem by Van den Dries and Miller that Rnx was o-minimal. What happens for the o-minimal structures is that even though it's a generalization of algebraic geometry, it is pretty close to algebraic geometry in how it behaves. If you have o-minimal things, still stuff behaves much like algebraic geometry. So first of all, you can develop a theory of, for example, definable topological spaces, right? That would be a topological space. You want to have a finite cover by open sets that are homeomorphic to subsets in R to the n. And then you want the intersections, on the intersections, you want the transition functions to be definable in the sense of your structure S. You can do definable manifolds, definable complex spaces, etc., all of these things. And if your structure is o-minimal, then this is pretty close to algebraic geometry and not at all close to general topology. So these spaces will have well-defined dimension. You can have finite cell decompositions with very nice cells. You get these good uniform finiteness statements that you're used to from algebraic geometry, etc., etc. Okay, so you can talk about things that are more general than algebraic varieties, but you still keep a lot of the results that are familiar from algebraic geometry. Okay, and so let me maybe get back to this theorem. So I've stated this one more time here, because I want to stress the definability now. So when I say this kind of locus of self-dual classes is definable, what it means is that, so it sits inside of this vector bundle E, which is an algebraic vector bundle. So E is an algebraic variety. In particular, it is a definable manifold over R alg, right? Because locally, E is a sub-variety of some C to the n. C to the n is R to the 2n. So this is an algebraic subset of R to the 2n. And then the transition functions are algebraics. In particular, they're functions that are definable in my structure R alg. And then this theorem is saying that if you enlarge your structure from R alg to this Rnx, then this locus becomes definable. So at the end of the day, this is saying something like this set, the conditions that define it are some kind of things like algebraic functions, restricted analytic functions, the real exponential function, stuff like that. Those are the kind of things that you need to describe the set. Okay. Any questions? Is the statement clear? Yeah. Yes.
Can you explain how does it follow that E is an algebraic variety?
So E is actually because E is originally like a holomorphic vector bundle. Right now it has a connection on it because it comes from a local system, and then any vector bundle, and then the sort of asymptotic stuff about variations of Hodge structure shows that that connection is well behaved at infinity. So then the bundle is algebraic and the connection is algebraic also. This is sort of some toy case of the Riemann-Hilbert correspondence or something like that.
But where do you use definability in this argument?
No, you don't. So the fact that the vector bundle is an algebraic vector bundle, this is just a consequence of basic Hodge theory, if you want.
Yeah. So,
but
I mean, you just wrote that what does definable mean here, and what the first is that it is a complex.
No, yeah. Sorry, no, I guess this is not clear. So when I say that this locus inside of this vector bundle is definable, what it means is that first of all, I consider this algebraic vector bundle as a definable manifold. Then I enlarge the structure to Rnx, and then in that manifold, which is definable over Rnx, this subset is a definable subset.
Okay. So
that's right. So when you say definable, originally it's a notion about R sets in R to the n. So I have to have some ambient space in which I'm sort of defining.
Okay. This is what you need to make sense about this definability. Okay.
Yes, exactly.
Thank you.
Yeah. Okay. Yeah, so now I'm gonna maybe do a thing that will not make anyone happy, which is give a sort of sketch of the proof. It's a maybe it's slightly too complicated for a talk, and I'm also slightly low energy now because it's late in the afternoon here, but anyway, let me give it a shot. So at least the good thing is that this argument is fairly conceptual compared to, say, Cattani-Deligne-Kaplan, which would be very hard to explain in a short amount of time. Okay, in particular, this of course gives a different, more conceptual proof for Cattani-Deligne-Kaplan, but I mean, this was already observed 2 years ago or so by these guys. So anyway, so the input of the proof is three things. So first, the big theorem by Bakker, Klingler, and Tsimerman, which says that for variations of Hodge structure, the period mappings are definable in this structure Rnx. And then to apply that, we need a bit of results about maps between arithmetic quotients and Siegel sets, and then some lattice theory. So for people who like K3 surfaces, maybe they like this lattice theory argument. Okay, so here's how it goes. Okay, so first of all, I need to set up a little bit of notation. So the thing is, we're used to, when we talk about Hodge structures and variations of Hodge structure, we're used to talking about period domains, because the period domain is sort of the moduli space for Hodge structures. In this theorem, we're actually not using the Hodge structure itself. We're only using the Weyl operator. Everything's just stated in terms of that. And it turns out that the Weyl operators still have some kind of moduli space, which is smaller than the period domain itself. It's a quotient of the period domain. It's a so-called associated symmetric space. So it's the set of real points of some reductive group modulo some maximal compact subgroup. So the way this works is that I first fix a reference point so that I get a fixed integral lattice, a fixed complex vector space, a fixed pairing on it, a fixed Weyl operator, and a fixed inner product. And then I compare all the other ones with this reference data. Okay, now in this case, I have a natural algebraic group, namely this group G. This is simply the orthogonal group of this pairing. And this is a reductive group defined over the integers, or the rational numbers if you want. The set of real points is just the real automorphisms of this vector space that preserve this pairing. And then because I have an inner product, I get a natural maximal compact subgroup as the stabilizer of this inner product. If you write it out, the condition is, because of the way the inner product is defined, it's just those elements that, when you conjugate the Weyl operator, leave the Weyl operator invariant. That's a maximal compact subgroup. And then the quotient space, G mod K, the points in there parameterize the Weyl operators. If I have a coset of K, it corresponds to the Weyl operator, which is the conjugate of C by that element G. And then K itself corresponds to the reference Weyl operator. Okay, and then because the stuff is defined over the integers, we also have this arithmetic subgroup gamma, which is just those elements of the group that have integer coefficients when you look at them on this integral lattice HC. Okay, and so then the first thing is, from the variation of Hodge structure that we started from, we get a sort of period mapping. But here we're not associating, we're not keeping track of the Hodge structure, but only of the Weyl operator. Right, so at every point in X, I have this vector space and the Weyl operator acting on it. And then I can use the underlying integral lattices to identify the different vector spaces with each other. And in this way, I can transfer all the Weyl operators onto Weyl operators on this fixed reference vector space. The price of it is that I have to mod out by the group gamma because of the identifications. Right? But so I get a period mapping that is basically associates to a point in X the Weyl operator on that fiber. And it goes into the quotient of the symmetric space by that group gamma. If you've seen period mappings before, usually in period mappings, you only mod out by the monodromy group because that's enough to make the identifications. So usually in these kind of motions, gamma is the monodromy group. Here, we're not using the monodromy group, but we're using this much bigger group gamma, which is this full arithmetic group. So we're actually modding out by a lot more than we have to mod out by. And this is one of the discoveries of Bakker, Klinglerzimmerman, that this is the thing that you ought to do. You should not mod out by the monodromy group, but you should mod out by this full arithmetic subgroup. So this will hopefully become clear in the next 2 slides why that's necessary. But anyway, so the big theorem that they proved maybe 2 years ago is that, first of all, this arithmetic quotient of the symmetric space by that arithmetic group, this has a natural structure of an R-alge definable manifold. But it is not an algebraic variety, right? We're not doing the period domain, we're doing G mod K. So this is not even a complex manifold anymore. But you can still talk about it using this definable language. And then secondly, and more importantly, this period mapping for the variation of Hodge structure is definable in this big structure Rnx. Okay, where again?
Can you point out the difference between this group and the monodromy group in the example of K3 surfaces that you gave?
Probably in the case of K3 surfaces, it's pretty close because I think the monodromy group probably has like some finite index in this. This is like the full orthogonal group in that case, right? Yeah. So in good cases where the moduli space has very high dimension, I think the monodromy group on the moduli space tends to be close to this big group. But if I just take like a variation of Hodge structure on some small base, then the monodromy group will be small and this group will be pretty big somehow.
It's related to the surjectivity, I think, in the K3, which is in Calabi-Yar threefolds, you don't have.
Yeah.
Okay, thank you.
Okay, so anyway, so this period mapping is definable. This is like the big input. The way this is proved is really by picking a good compactification of X, studying how the period mapping looks like at infinity, and showing that it can be described using certain kinds of functions. So that uses as input all of these results from the 80s about variations of Hodge structure on the complement of a normal crossing divisor and so on. But the good thing for someone who's not an expert in Hodge theory, but the bad thing for me maybe, is that this is a sort of black box that takes all of that stuff from the 80s and gives you one nice, clean, easy to remember statement, right? The period mapping is definable. Once you have this statement, you pretty much never have to go back and look at the nitty-gritty of variations of Hodge structure anymore. So this is a really strong result. Okay. Now we need something slightly more general because we're not just looking at sets in X, but we're looking at sets in this bundle. But this is quite easy to do. So first of all, it turns out that over this arithmetic quotient, I can put a sort of universal Hodge bundle over it, whose fiber is this fixed vector space HC. So the way you can do this concretely is you take the symmetric space, cross the vector space, and then you mod out by gamma, where gamma also acts in the vector space, right? And here's the action. So gamma acts on the coset by translation, and it acts on the vector space by just the corresponding matrix. And then it turns out that this quotient here, when you map down to the arithmetic quotient, that's kind of universal vector bundle with fiber HC. The period mapping can be lifted to a map from the Hodge bundle to this universal Hodge bundle. And this definability here implies quite easily that this lifted map is also definable. Okay, so this universal bundle is still our Alge definable, and the map from our given Hodge bundle to the universal bundle is still definable in RMX. Okay, and then the good thing about this is that once you have this, it completely changes the problem. Originally, it's a problem about a variation of Hodge structure and some loci defined by it. Now it just becomes a question about algebraic groups. And because now, inside of this universal bundle, we can look at the locus of self-dual classes inside of there. If we manage to show that locus of self-dual classes in this universal bundle, that's definable, then the locus that we care about is the inverse image of something definable under a definable map. So it will be a definable set. Okay? So we just have to show that the set of self-dual classes in this universal bundle is definable. And that actually happens in the smaller structure R Alge. So we've gone from what used to be like a sort of study this locus near the boundary in a compactification to some nitty-gritty sort of local analysis of how it behaves and so on. You completely change the problem to study this universal locus inside of this quotient of some algebraic group and see what you can say about it. It's completely different now, right? Okay, anyway, so this universal locus will look like this. So this will be points in this universal bundle that are self-dual Hodge classes at the bounded value of the pairing. So since I'm maybe slightly too tight to my notation here, but anyway, so the points in the bundle are these cosets, which are basically remembering the Weyl operator and the vector. And the condition is that the vector should be integral, it should be self-dual for this Weyl operator, and then it should have a fixed value of the pairing. So I want to explain why this locus is definable in the structure Alge. Okay. And then, well, the first objection is this can't possibly be true because, well, the condition to be definable means in particular that I can never have any infinite discrete sets. Because in dimension 1, the only definable thing is supposed to be either integrals or finite unions of points. Anything that's infinite and discrete is deadly for definability. But in this set, I'm allowing any integral vector, right? V can be any integer vector in this HC, and HC is, of course, infinite discrete. So this looks kind of fishy, right? Okay, and so here is, there's a first sort of miracle that happens, which is a result from lattice theory. So the miracle is that this condition QVV fixed, even though this still leaves you with an infinite discrete set, this leaves you with a set which is a finite union of orbits of this group. Okay, so precisely the result from lattice theory, this is, I guess, a theorem by Minkowski in some way, but the most general thing is in this book by Kneser, so I'm just attributing it to Kneser. So it's, if you have a lattice, so in this HZ with a symmetric form on it, and then you look at the set of integral classes on which this form has a fixed value, that set, even though it's infinite, is a union of finitely many orbits under the orthogonal group. The orthogonal group being this group gamma in our case. Okay, so this is really the reason why we have to use this full orthogonal group, the full arithmetic group, and not just the monodromy group, because this would be not true for the monodromy group. So this is good because it means that instead of considering all infinitely many integral vectors, we just have finitely many orbits of gamma, and then we can just focus on one of the orbits. If you can show that one of the gamma orbits is definable, then the whole thing is a finite union, so it's still definable. Okay, so now we just consider one gamma orbit. So one gamma orbit means I fix one particular integer vector. I can assume that it's an eigenvector for the Weyl operator, because otherwise the locus would be empty. And then I just look at the set of self-dual classes in that fixed orbit. So the integral class is now in the orbit of this fixed vector, and it's still self-dual under the Weyl operator. And then this condition on Q is automatic because Q is constant on the whole orbit. And so let me explain why this locus is definable. Okay. Right. So a small addition to the notation from above. So that this symmetric space, the points of that corresponded to the Weyl operators. Once I have this class A, I can have a smaller symmetric space. So first I have a subgroup, which is the subgroup of things in G that fix this vector A. This I denote by G sub A. And then I also have a corresponding maximal compact subgroup, Ka, and so on. The symmetric space of the smaller subgroup, Ga mod Ka, is naturally a subset of this bigger symmetric space. And the points of that smaller symmetric space correspond to Weyl operators that fix A. This is a little calculation I have to do. Okay, and so now I'm going to use this group to define this locus. So I'm going to actually give a sort of, I'm going to show that the locus of these self-dual points is actually basically itself a symmetric space coming from the smaller group. Okay, and so here's the calculation that you have to do for that. So the calculation is, let's take a class in this orbit, a self-dual class in this orbit. Okay, so the integral class V is in this orbit, so it's of the form gamma times A, and then I assume that it's self-dual, so this condition. Well, if I plug in V for that, I can rewrite the condition like this. And so this means that the Weyl operator, which I get by conjugating by gamma inverse times G, that fixes A. And so that Weyl operator is itself a conjugate of my reference Weyl operator by some element that fixes A. So I get this identity here. And then if I rewrite this, it says that H inverse gamma inverse G stabilizes C under conjugation. So that's an element in the maximal compact subgroup K. And so therefore my coset is actually, up to translation by gamma, a coset of the smaller group GA. Okay. So therefore, this orbit that I'm interested in, the orbit of this point, can actually be written as the orbit of a special point, where the integral class is just this fixed class A, and the coset is a coset by an element in the smaller group GA. And so what this is saying is that the locus of self-dual classes in this fixed orbit is actually all points where the second component is this fixed vector A and the first component is a coset by the smaller subgroup. And so the conclusion is that anyway, that this locus of self-dual classes in this orbit is just the image of the smaller arithmetic quotient here. I take the smaller symmetric space GA mod KA, I mod it by the smaller arithmetic group gamma A, and that maps into this bundle. And the calculation here shows that the image of that map is exactly the locus that I care about. And in fact, it's an embedding, and so it's the locus that I care about really is it's itself like an arithmetic quotient. Okay, so in fact, you have this diagram here. So you have this big arithmetic quotient that you care about, the smaller arithmetic quotient here for the subgroup, and it's the smaller arithmetic quotient that gives us our set. And so then the way we get definability is just by another general theorem. This is again in this paper by Bakker, Klinglerzimmerman. Namely, the theorem is the following, that if I have so I have this arithmetic quotient for the big group G, and then I have the smaller arithmetic quotient for the smaller group GA. And the theorem is that the map between the groups induces a map between the arithmetic quotients, and that map is definable in our algebra. Okay, and so then again, modulo worrying about the lifting into this vector bundle, this gives you the definability of this map up here. Therefore, the image is definable, but the image is the set that we care about. So therefore, the set is definable. Okay, so this is quite nice because, again, in Cattani-Deligne-Kaplan, the way you show that something is algebraic is you go to a compactification, you do some very careful nitty-gritty analysis of what happens in the compactification to show that the thing is analytic in a compactification, and then it's algebraic by Chow's theorem. Here it's quite different, right? Here we translate the problem into some kind of universal problem about arithmetic groups, algebraic groups, and then it turns out that our locus is itself the image of coming from some map between algebraic groups, and then it's definable because of that. Okay, so it's a much more global argument. There's no local analysis whatsoever. Okay, now I have one more slide about some technical details. Sorry if maybe I've already lost everyone. So there's a small subtlety here in that in the paper by Bakker, Klinglerzimmerman, they said the following. So they said that whenever you have a map between two reductive groups, for example, this group G and the subgroup GA, and you look at some small condition, and then it induces a map between arithmetic quotients, and that map is definable. And that, unfortunately, that's slightly too strong. That turns out to be not quite true. So it turns out that there's actually a condition that's needed, which is satisfied in our case, but maybe it's not always true. And so I want to at least say on this slide, sort of when you say this kind of thing, that something is definable and that the map is definable, what does it actually amount to? What do you actually have to show? So again, there's a small subtlety because when you say that this arithmetic quotient is an R-alge definable manifold, this is more complicated than it looks because it involves a quotient by a group gamma, and gamma is infinite and discrete. Okay, so the way that this works is not by saying, well, how to say? So like a naive approach would be like this, right? G of R is the set of real points of an algebraic group. That's clearly a real algebraic, an R-alge definable manifold. The quotient by K is an R-alge definable manifold. But then you quotient out by gamma, and gamma is infinite discrete. So then you leave the world of definable stuff. So this is not how the quotient is taken. Instead, you take the quotient by finding a good sort of fundamental set and taking the quotient of the fundamental set. And this involves what is classically known as reduction theory for arithmetic groups. There's a big book by Borel that discusses that. So what you do is you find a so-called Siegel set. A Siegel set is a certain kind of semi-algebraic set in a real group whose image in G mod K gives you almost a fundamental domain for the gamma action. More precisely, you have the Siegel property. So when you look at translates of the Siegel set sigma, you can only intersect finitely many translates by gamma. So in other words, the sigma is not quite a fundamental domain, but on sigma, the equivalence relation defined by gamma has finite fibers. And then you can take a quotient. So when you say GR mod K mod gamma is definable, it is really saying that first you take a Siegel set that's semi-algebraic, then you take a quotient by this finite equivalence relation, and that gives you the structure on the quotient. An example of a Siegel set, well, the definition is somewhat complicated, but so the simple example is the upper half plane, right? So if I take the group SO2, the maximal compact SO2, then this is what the fundamental domains look like. And then the Siegel set is a kind of simple set. Again, let me draw this here. So a Siegel set would be a set that looks something like this. This is the kind of set that you allow. Okay, so you're not taking the fundamental domain because it's kind of complicated to do in higher dimensions, but it turns out that there's a class of sets that are easily describable by some algebraic conditions or semi-algebraic conditions that in this sort of case look like this. Imaginary part greater or equal to something, real part bounded between two things. And you will only then intersect finitely many fundamental domains. And then for this definable business here, what you have to then show is that when you say that a morphism of arithmetic quotients is definable, what it really is a statement about Siegel sets. So what you have to do is you have to show that any Siegel set in the smaller group GA, when you map it into the bigger group G, it lands in a union of at most finitely many Siegel sets. And then you get finiteness and you get the sort of stuff that you need for definability. In the case of our specific groups, the orthogonal group of that pairing Q and the subgroup, you can check by hand that this thing about Siegel sets works. Any Siegel set in GA actually maps into a union of at most two Siegel sets in G of R. And then there's also a general theorem by this guy Martin Orr that takes care of it. When we're doing this project, we sort of discovered these small gaps sort of in the literature. So this theorem was stated slightly, or this was a little more general. The statement was a little bit more general than it's actually true and so on. But anyway, this is all fixed now. So now this you can easily get definability of these maps. Okay, and so that's how it works. Okay, so I guess that's the end of my talk. So thank you very much. Yeah, if I can go to the next slide. I cannot.
Let's all thank Kristen. Are there questions?
So can I ask? I mean, does your method also give an alternate proof of the classical theorem?
Yes, indeed. Yeah, right. Because as I said, so the classical Hodge loci, they will be some of the components of these self-dual loci, right? So then you need one more step, which is that if something is definable in an o-minimal structure and it is also complex analytic, then it is actually complex algebraic. That's a definable version of Chow's theorem, which again was proved by logicians, by Petersil and Starchenko. But this goes without compactness, right? So it's just definable and analytic implies algebraic. So then in particular, you get another proof of Cattani-Deligne-Kaplan. So the way this collaboration sort of happened is that Bakker and Tsimerman, they already observed this fact that by this definable stuff, you can get a new proof of Cattani-Deligne-Kaplan. And so then, they didn't quite write out the arguments. They sort of only had it in their heads somehow. And so we put it all together into one paper. Yeah.
But how do you pull back under the period map? Isn't that not definable in RL?
The period mapping is not definable in RL. Exactly. For that you really need the exponential function and so on. I
was wondering in the alternate proof of Cattani-Deligne-Kaplan, how do you take care of that?
So it's the same story as here, right? So you don't go to the period domain, but you go to this quotient G mod K, and then G mod K mod gamma. Inside of there, you have these sort of universal loci, which are the universal Hodge loci, and they're not complex analytic in that case because that space isn't even a complex manifold, right? But they're definable in our algebra by basically the same argument. And then their inverse image under the period mapping is now definable. And then independently of that, by just local analysis, it is complex analytic. And then those two things together give you algebraicity. So you're still not doing any local study, right? You're still inside of the quotient of the period domain. You have these universally defined sets, which are definable by algebraic equations, but over the reals, and then you pull them back and you get definability. Yeah.
Are there other
Can I ask a question?
Go ahead.
Yeah, please.
So how does this period map from X to G mod K mod gamma compare to the classifying map when you view the Hodge metric as harmonic metric? But that goes to...
Yeah, it is exactly that. Yeah.
Okay.
Except that the group is slightly smaller. So right. So if you know about harmonic bundles, a variation of Hodge structure is an example of a harmonic bundle. A harmonic bundle also has some kind of classifying map, which goes into GLN modulo some unitary subgroup. And here we're remembering the pairing. So we go into the smaller group G of R instead of going into the full GLN. But modulo the embedding of G mod K into GLN mod the unitary group, this is exactly the classifying map of the harmonic metric. Mm-hmm. Yeah.
Thanks.
Other questions?
Can I make one more comment? Sorry. So I want to really, I don't know if maybe I didn't get this across, but I really want to stress this point very strongly. So this project has sort of totally converted me to this viewpoint, right? Like when I started this project, I didn't know what a Siegel set is. Surely I don't know like what a parabolic subgroup of an algebraic group is and stuff like that, right? So, but I used to be an expert in this sort of local analysis of variations of Hodge structure, that sort of stuff, like all of these careful theorems that tell you how a VHS degenerates.
I think you still are, Christian.
Huh?
I think
Yeah, okay,
maybe
I still am, but this expertise has suddenly become unnecessary, right? Because now you have this definability theorem that hides all of that technical stuff into this statement. So this is like some of this really big shift that you used to have to do these things by hand, locally, in each case individually, and now you have this one uniform, general purpose theorem that takes care of that. So this is really something to make a mental note of, that some of the stuff has shifted in that area.
So you said there's not really a geometric interpretation for these self-dual classes.
Yes.
But I mean, is there some kind of candidate Hodge conjecture type statement for these self-dual classes? I mean, obviously not that they correspond to something algebraic, but that somehow, I don't know, on the, in the geometric side, there's some definable criterion that gives you an interpretation of these self-dual classes.
Yeah, it's a good question. Yeah. I don't know. I don't know. I mean, certainly, if there is something, it wouldn't be complex algebraic geometry, right? So, because of all the sets you see there are just Hodge classes.
Right.
I don't know. I mean, one could speculate that maybe if you go to certain real algebraic subvarieties or something like that, but I don't know of any examples. Let's say. So I don't know. I mean, one could take something like maybe K3s, I guess. For K3s, do self-dual class, anti-self-dual classes of type 2, 0, and 0, 2, and see if there's any sort of description of what they are. I don't know.
Are there any other questions?
Are there any other definable sets in the period domain that we should be thinking of?
It's a good question, yeah. I mean, so I guess this takes care of sort of all the sets that you can define using the Weyl operator, basically. So I suppose, I mean, you could imagine putting some other conditions on the Hodge decomposition that involve more than the Weyl operator. So not just fixing the Hodge type of the class, but maybe saying something like, you know, the 2-1 component of the class is 3 times as big as this other class, or things like that. I mean, this would presumably also give you definable sets. Because I mean, the Hodge decomposition varies in a definable way from point to point and so on. But yeah, I mean, then you have even less. I mean, here sort of, I believe probably once this catches on, maybe the physicists will probably do some more thinking about what this actually means in their world. And then maybe in a couple of years, one will know some more precise conjectures about these self-dual classes. But if you put some more general conditions, it's not clear to me that you get anything meaningful.
Maybe I can just mention that this condition that there are integral classes in H20 diagram H02 for hyperkähler appear in Verbitsky's papers, where it's ergodicity papers, where it's a condition where the orbit under the arithmetic group fails to be dense. It's precisely, it appears in an erratum of his to a paper.
Okay.
First he said that the only failure is when the Hodge structure is defined over Q, but then he corrected it to say that precisely the condition is that there is an integral class in H20 diagram H02.
Okay, thank you. Yeah, I should. I will look that up. Thanks.
You're welcome.
Okay, so well, maybe let's thank Christian again. That was, yeah, very good.
You're welcome.
And there will still